Morning. So this is a question that was asked in GATE 2019. So the question reads: the magnetic circuit shown has a uniform cross-section area and air gap of length zero point 0.2 centimeter. So this air gap of length 0.2 centimeter, here we have written the mean path length of the core is 40 centimeter. So this mean path length is represented by Lm, that is shown here 40 centimeter. Assume leakage and friendly fluxes are negligible. No. When the core relative permittivity is assumed to be infinite, so relative permittivity of the core, that is your mu r, is assumed to be infinite, that is infinity. The magnetic flux density computed in the air gap. Magnetic flux density means what? Flux density is Bm, that is your flux by area. Your magnetic flux density is given by flux by area. Current density similarly is current by area. Flux density is flux by area. So okay, is Bm is 1 Tesla when your mu r. So we came to know that our value of Bm is 1 Tesla when my what, when my mu r is equal to infinite. So this is the case. Okay, now what the question says is, so the magnetic flux density in the air gap is 1 Tesla. So with the same number of ampere turns, so ampere turns means current into number of turns of the transformer. These current and ampere turns also reflects mmf, and in the magnetic terminology this is linked with your voltage also. So if you can see my lecture first, wherein I am discussing about ampere turns, mmf turns ratio, you please visit that very first lecture of mine. And in the networks also I have discussed about the inductance calculations. Please have a visit, because what GATE does, it puts two concepts into one and tries to test you. So with the same, if the core relative permeability is assumed to be 1000, so now this everything is same, flux density, ampere turns is same, and the cross sectional area is same. Now what we are doing is mu r, we are assuming it to be 1000. So 1000, the flux density in Tesla, and now when this is at 1000, now what is the flux density at that particular point? What is the flux density? So for the same mmf, we know that mmf is what? Mmf is an electrical equivalent of voltage. So voltage is given by current, your mmf current into resistance. So your mmf would be your current I into R, that is flux into reluctance. So this is the magnetic equivalent of flux, is the magnetic equivalent of current, and reluctance is the magnetic equivalent of resistance, and mmf is the magnetic equivalent of voltage. So this we have already seen. So from this equation, mmf symbol is like this. Mmf can be written as phi into reluctance, or in other terms your flux can be written as this mmf divided by your reluctance. So your 1 by reluctance is called as permeance and represented by S. In some books it is represented by this denomination. So we are so now the number one thing is that reluctance in the first case. What would be the reluctance in the first case? So here we'll keep certain things. So we know that your mmf, or we can write our flux is mmf into your reluctance, that we just saw in this equation. Just we saw your flux is mmf by reluctance, we just saw in the equation. And what is mmf? Mmf is the total number of ampere turns. So these things we have to keep in mind before going to the solution of this problem. And so side I have kept these points. Have to be very careful when we are doing these things. So now the thing is that let's see. So from here I can see my flux is proportional to my mmf by reluctance, or it is inversely proportional to my reluctance. That thing I can see. So in case 1, what it states is that in case 1, how is my reluctance given? The value of reluctance, the value of resistance is given as rho L by A. So the value of reluctance is given as same thing, where L is length, A is area of cross-section, L A by C, 1 by rho. This rho we can write here rho or 1 by rho. This 1 by rho, if it goes top, this 1 by rho is called as mu naught. So this 1 by rho is called as LA mu naught. So this is that thing. This is the permeability of a free space. So this reluctance depends upon your length of mu turn mu naught into A, which in turn depends upon your length of the air gap. So in the air, the relative permeability of the air will come, that is mu naught into A, plus length of the mean turn, same thing, mu naught into mu r, relative permeability of the medium into A will come. So in the first case, it says, case number 1, it says my mu r is equal to infinite. So in case when my mu r, if I put the value infinity, 1 divided by infinity, this thing will go, it will become 0. So my first case, my reluctance 1 will come around how much? My reluctance 1 will come out only length of mean turn mu into A. So length of mean turn is 2 centimeter. If I convert the centimeter, 0.2 centimeter into meter, so how can I write this? I can write 0.2 into 10 power minus 2 meter and divide by mu naught A. So this is my length of mu naught I am getting. This is my equation 1. So let's see now. Now what should I do? Now the case 2 I have to consider. This is case 1. Okay, case 1. What about case 2? Case 2, again the same formula. If this is R1, what about the R2? Here mu r is not equal to 0. Is it infinite? It is given mu r is 1000 in this case. So we have to account. So we have to account both the things. We have to account length of the air gap mu naught A plus length of the mean turn mu naught mu r into A. So here I have to account both the things. So here length of the air gap, again what it was, 0.2 in 10 power minus 2. This will be mu naught A. Instead of mu r, I will replace it by 1000. So I'll get length of mean turn, again it is 40 centimeters. So 40 into 10 power minus 2, 40 into 10 power minus 2. This is 1000 mu naught A. Now this equation, if I simplify this equation, I'll get a value. If I simplify the equation, I'll get a value is equal to, this value would be equal to 0.24 into 10 power minus 2 mu naught A. So this is my value of my reluctance 2. My reluctance 1, I calculated my reluctance 1 and I got a value of 0.2 in 10 power minus 2 divided by how much? Divided by mu naught A. So this is my reluctance 1, this is my reluctance 2. So what it's asking us, so in the first case my flux was 1 Tesla. So now I know that my flux is my proportional to my B. See, because your flux is proportional to your current density, B is proportional to your flux by area. So area of cross section remaining constant. So it is proportional to your flux. So in and flux is proportional to your magnetic density, whereas your flux is inversely proportional to your reluctance. Flux is inversely proportional to your reluctance. In other terms, you can write my magnetic field density is inversely proportional to your reluctance. So you can safely write B1 would be inversely proportional. Now you got these values. So this is R1, this is R2. So we'll be rubbing this and I'll be explaining from here. So these values will keep as it is. So one thing we saw, our flux is directly proportional to your flux is equal to mmf by reluctance. Okay, so flux we can say is proportional to flux of 1 by r reluctance of 1. That thing is there. And one more thing is your flux is equal to your magnetic field density. Your B is equal to flux by area. So your B1 is directly proportional to your phi1. So you can directly write your B1 is proportional to 1 by R1. Similarly, from this inference you can write your B2 is directly proportional to 1 by R2. So B1 value is given 1 Tesla. So you can write B1 by B2 is equal to 1 by R1 divided by 1 by R2. So this is 1 by R1 into R2. This is R1 R2. So how much it will become? From here you can write B1 by B2 is equal to R2 by R1. B1 value is given. B1 value is given. How much it is given? B1 value is given, so you need to calculate the value of B2. So once you get these values, you substitute in the equation and you just check for yourself the values. So by now most of you must have solved it. So just now we saw that B1 value is given, that is 1, and you need to calculate the B2 value. So how do you calculate the B2 value? So from this one only you can calculate here. From this equation only you can calculate. So you can write B2 is equal to R1 into B1 divided by R2. So B1 value you have is 1, R1 value you have calculated is 0.2 into 10 power minus 2 mu naught A. Now into R2 value 0.24 into 10 power minus 2 mu naught A. So this mu naught A cancels. So you are left with this 1 into 0.2 in 10 power minus 2. So 10 power minus 2, 10 power minus 2 cancels. So you are left with 2 by 24, or this is 1 by 10, okay, and this 24 is 1 by 100. So you have 2 by 0.24. Now if you calculate this, you get around value of 0.833 Tesla. So here the calculation part you can do in the calculator also. So you get the value of 0.833 Tesla. Hope you have understood the problem. So it was a simple problem. It was just based upon your knowledge of your magnetic field, flux, reluctance. Similarly, so some problems will be there, like there is one problem here that has been appeared in an examination. So this problem particularly is based upon your knowledge of your relationship between your reluctance and your inductance. What is the inductance value, which we have calculated earlier also. You can see these values. So I want you people to do on your own. If you are not getting it, I'll be substituting. So this is your homework problem. So please do the homework problem and try to do this problem. This is the homework problem for you. I'll read out the problem. So yes, it can be a little blur. Yeah, a single phase 10 kVA 50 Hz transformer with a 1 kV primary winding draws 0.5 ampere and 55 watt at rated voltage and frequency on no load. A second transformer has a core with all its linear dimension √2 times the corresponding dimensions of the first transformer. So of the first transformer, the core material and lamination thickness are the same in both the transformers. The primary windings of both the transformers have the same number of turns. If a rated voltage of 2 kVA at 50 Hz is applied to the primary of the secondary transformer, then the no load current and power respectively are. So this is your homework problem. Thank you very much. If you are not getting it, you can contact me. I'll solve it for you.